So, how did we get to this crazy situation where you have these weird societies? Well, in Hymenoptera, the ancestors were parasitoids. Now, this is a parasitoid. If you take insect biology, we're going to learn loads about parasitoids. What they do is they lay their egg inside another animal, inside another insect, and the egg develops inside that insect, in many cases while it's still alive, kind of swimming around inside the hemolymph of the other insect. And so they're used to being bathed in a sea of fluid which is of perfect concentration for development. The eusocial Hymenoptera have evolved out of that situation, and their larvae now don't develop inside other individuals. So they had previously become helpless grubs kind of swimming in this sea of the host organism's blood, and now they've been untimely ripped out of those hosts, and they are now helpless white grubs and entirely dependent on parental care. So clearly they're incapable of dispersing before they're adults, and so this selects very, very much for parental care between the parents and the offspring. The parents have to attend constantly to their helpless white grubs, and it selects for the building of nests that protect those helpless white grubs. So that's why we think these extended nests evolved in the Hymenoptera. They're for parental care. And so this is a very classic sub-social situation with helpers at the nest. You start off with solitary parasitoids. After they evolve to come out of that host, there's then nest guarding by the female. The young are selected to stay behind and help care for more young, and then the young become a worker caste. So you start with generation. If you think about those criteria for the evolution of sociality that Michener proposed, in this case you'd start off with generation overlap, you'd then evolve cooperation, and then eventually you'd evolve caste systems. In other Hymenoptera, you've got situations where you have this plural breeding situation. So you've got, like for example, we were describing in the thrips, where several reproductive females cooperate, and then they start off with nests in the same place, kind of solitary females all nesting in the same place, and then something selects for cooperative nest building or kind of nest defense, and then one of those females comes to be dominant, and the others, and then the young of that female will become the workers. So in quite a lot of ants you'll get cooperative nest building by females, which then one of them they have a fight and one of them becomes dominant, and the young then become the workers. So in this situation, you start off with cooperation among females, then you get castes, and eventually you get the generational overlap. So there's a couple of different routes to sociality, to the evolution of eusociality there. And two examples of these. So you've got you have things that exemplify the very early evolution of those things. Are these kind of carpenter bees, for example? These giant black bees that have one offspring that tends to stay behind and help the mother produce a few more offspring in one nest. The Halictus bees that we met in the last lecture. Lots and lots of bees have a very primitively eusocial setup where offspring will stay behind and help mother. And then primitively semi-social setup with paper wasps, where females will cooperate to make this nest here, and after the nest has started they'll have a fight, and the outcome of the fight determines who gets to produce all the offspring, and the other females just kind of then wait peacefully in a queue to see if the queen will die. By contrast, cockroaches have a completely, termites have a completely different origin story. The origin story of cockroaches is they started off as these things called wood roaches, which feed exclusively on wood, and they need, as I said in the last lecture, they need these bacteria in order to digest the wood. They need endosymbionts, and they pass on those symbionts by this trophallaxis, by feeding on each other's feces, which is extremely delightful. So you start with families of cockroaches in which the female transfers protozoa to the young. That then evolves to a situation where the young stay behind and help defend the nest and care for the younger offspring. That leads to a situation where the young become workers. So, and there you have your typical termite situation. So you start off with generational overlap, then you get cooperation, then you get castes. So it's several different routes towards sociality. An interesting case to mention is these damp wood, these dry wood termites, Zootermopsis, which live in blocks of wood. And when they colonize a block of wood, they will chew the wood and they'll listen to the echoes produced in the wood. And they have mechanisms to measure the size of their block of wood using echolocation, which I think is really, really cool. So they know how much resource they've got to go on based on the echoes that their chewing makes. Okay, back to the route for social evolution. There's a key distinction made by Queller and Strassman here of what kind of sociality. There are kind of two major kinds of eusocial evolution that they identify, and this is very useful for when you think outside of the box of just ants and termites, because ants and termites embody each of these, and other eusocial societies can fall into either of these boxes. So they suggest that we can divide eusocial societies into fortress defense, which is soldiers coming first. So these are individuals that live within a resource which is valuable and defensible. And they get all their food from inside the nest, and they tend to have kind of active larvae, which like the larvae constitute the helpers, and they can feed themselves and they can help. Usually, this ends up in a small colony inside a defensible resource, like a gall. So that's a thrips gall, that's an aphid gall. Each of those have a soldier caste which defend the gall. And then you have life insurance, where, as we suggested, the first thing that happens is you get a parental care evolving. So the initial function of a caste is to provide parental care and to forage for the offspring. So this is all ants, bees, and wasps, and the main advantage of grouping is to provide generational overlap that provides a extended parental care. They tend to get their food from outside the nest, which requires the foragers to be the workers to be foragers, and the juveniles are not very useful. They're helpless, as they need to be fed, and the whole thing revolves around the need for parental care. Eventually, once evolution has started down that road towards the evolution of societies, Wilson and Holdobler proposed that you then get a point of no return. You get primitive eusociality along either of those tracks, and then you get this point of no return where you then get commitment to physical castes, and then the evolution of advanced eusociality, where workers commit to being sterile and only helping them, the queen, produce more offspring. This is a nice paper. The argument is very much from the point of view of multi-level selection, and I would say this is, like, it sounds plausible. Like this point of no return is the point at which selection at the level of the group begins to tip over, such that selection at the group level is more important than selection at the individual level. I would encourage skepticism of like healthy skepticism of this. It's a nice idea. I'm going to put a great bag of beans on the idea of a point of no return. We're going to come back to that in the next and final lecture on social behaviour, and I'll explain why in that next lecture. But the idea that there's a point of no return is an intriguing one. It intuitively kind of conjures up a major transition in evolution, which is an interesting idea.